Hi, I would like to welcome you to my tutorial about graphs versus Python within RealFlow. Within this tutorial, I'm going to describe here the differences and similarities between graphs and Python, and each of these programming environments got their benefits and drawbacks, and I think knowing them will improve your workflow immensely. At the end of the tutorial, I'm going to show you an example of solving exactly the same problem, once with graphs, once with Python. And during doing that, I'm going to show you the differences and point out some important facts. In principle, this example at the end is kind of a theoretical one, because in practice you probably will not transform your Python code directly into graphs. Instead, you will solve some problems which are well suited for solving with graphs using graphs, and you mix all that up with using Python code for some other problems, and showing you for which purposes both environments are created. This tutorial is made. It's important to point out that this tutorial aimed at persons who know how to program within Python. If you never have used Python, you can go directly to programming with graphs, and this tutorial is kind of not important for you. So, what are the commonalities? Both graphs and Pythons are programming environments, and they're intended to solve some individual problems which are not possible to solve directly out of the box within RealFlow, and we think that add a lot of flexibility to the whole RealFlow environment. Both programming environments get access to all RealFlow data types within the scene, and what I really like to point out is that mixing of both concepts within the graph flow is possible. So you can apply the environment which suits best to your actual problem, and this is kind of a very general approach and adds a lot of flexibility. Well, what are the differences? Graphs are basically node-based and provide a graphical interface, like nowadays a lot of other graphical packages provide. Well, Python is a script language, text-based coding environment, and since we know that artists do not really appreciate text-based coding normally, we thought graphs adds a lot of flexibility without writing a single line of code. Well, we know in Python there are functions. It's a functions-based programming language. In graphs we got a similar concept. We got compounds, which also provide an interface to a bunch of operations, and the good thing is that they can be shared and reused at will. Well, graphs are made mainly for accessing high-level compounds, which make your life a lot easier. And with Python you get the total low-level access, which is basically greater flexibility, but makes your life at certain points kind of harder, and you have to struggle with some programming problems which might at certain circumstances hard to use. On the other hand, graphs are multi-threaded, which is a great performance improvement nowadays. Python in general is single-threaded. If you program with graphs, you get arrays and conditions, and in Python you normally think in loops and branches. We got another tutorial about arrays, and I would really recommend that for showing you the differences between those both concepts. Just would like to point out that using arrays and conditions would improve the performance of your developed graphs quite immensely. And another similarity, for example, is in Python you got commands commenting your code and stuff, and in graphs you got some visual nodes which do basically the same, making groups and commands within the graph scene to keep your code clean. Well, I would recommend different main aims for graphs in Python. So I already mentioned with graphs, we got the high-level access, and we got a lot of nodes working on images, for instance, distance fields, and you can download additional functionality and even upload your own compounds to share them to the community. And in Python, we got a low-level access. Python is well made for parsing, writing your own exporter-importer functions. Doing low-level math is also much more comfortable using Python. And accessing layers, for example, is at the moment not possible within graph nodes. But the best thing, I think, is you can mix both approaches within the simulation flow, which means you can do some tasks using graphs and then write a parser in Python, and afterwards do something within random data types within graphs. This is a real flexible concept, and I would highly recommend using that approach. Let's get started. In the following, I'm going to demonstrate you how to transform that Python code into a graph node system. So what do we have on the scene? We got a linear emitter over here and a gravity and a sphere object. What the Python code is doing, I show you over here, is basically just doing a basic kind of collision handling. It's checking if particles are lying within the sphere, and if so, the particles are moved to the surface of the sphere. As you might see, there's no connection between the sphere and the emitter, so all this collision handling is done within the Python code. So what do we have over here? In the Python code, we first get the emitter, the linear one, and then get the particle system over here. Afterwards, we get a sphere 1, and get the position and the scale x, which is basically the doubled radius of the sphere. So I multiply it with 0.5 to get the real radius. Afterwards, we loop over all particles within the system and get their position. Then we determine the direction vector between the center of sphere to the particle position simply by subtracting the vectors. And finally determine the distance between the actual particle's position and the center of the sphere using the module. So the decision if the particles lying within the sphere's radius is fulfilled over here, and if this condition is true, we know the particle lies within the sphere, so we have to determine the new position on the sphere's surface, which is basically done by normalizing the direction of the sphere's center to the particle's position and scaling this with the sphere's radius. Adding that to the sphere's center is resulting in exactly the position of the particle on the sphere's surface. And at the end, we finally set the position. That's pretty much it. So let me create a new graph node system. Well, I've done my homework and made the Python code slightly more colorful here on the left hand, and I will use that color encoding in the following for the graph node system to point out clearly which part of the graph is related to which part of the code over here. So you see in the first yellow box we got our emitter linear 1 and get the particle. Basically we can do exactly the same within our graph node system. Thus I get the standard emitter and get the particles. Alright, and this is exactly what we do in the yellow box. Okay, this second box is the green one. So let's create a green box over here. And what we do there is we get the object. So check out the get object node over here, and we need the sphere all1. So we get the sphere all1. Afterwards we get the position and the scale x over the get parameter node. I copy it to get it tried and connected. Here we get the position, and over here we get the scale x. As I said before, we're multiplying the scale x with 0.5. So let's do the same within the graph nodes. We need a real constant over here and multiply it with our scale. Set the real to 0.5. And here we go. In the following, we loop over all particles. And this is one of the main differences between graph nodes and Python. And I would highly recommend the other video tutorial about arrays, where this difference is described briefly. The main point is the graph node system always works on arrays. So if we get a bunch of vectors or particle positions stored in an array, the following function will work on all that. So if we got here a particle get channel node and put in here the position, then we get an array of all particles positions within the scene. And the good thing is that the following nodes work on that array, so we don't have to include the for loop explicitly. Make the graph system kind of easier than the Python code. Alright, over here in the blue box we finally get the distance between the center of the sphere and the particle. First by subtracting over here the particle position from the sphere position, so we need a subtract node, and we subtract the particle position which we got over here from the sphere center, which we have gotten over there. Add a note for making the visualization more clear. All right. Then we get the direction module, which is basically the length of the vector. Okay. So we got all that. Afterwards, we check the distance to the sphere radius. And if the distance is less than the sphere's radius, we determine the new position on the surface of the sphere and set the new position. So let me do this first, and afterwards we add the if condition. So I add a note like that, make it slightly bigger, and we have here a normalization. So create a normalization node. The scaling is basically just a multiplication of a vector with a real over here. And finally, we add the two vectors. So we plug it in here. To keep at this point that part of the graph node system very general and kind of separated from the other parts of the graph, I add here a path through node. So what we need is first the direction. Let me rename that here to direction. And the direction will be normalized. So we plug it in over here. Then we need the sphere's radius. I create that here and connect that to the multiplication node. And finally, in that part of the code, we need the sphere position. type it here and add that to the add node. So in this part, we basically determine the new position only for the cases where the particles lie within the sphere. At the end, we here set the position of the particle. For that, we need the set particle channel node and set the channel position. All right, let me create another node over here to make that clear. Okay, finally connect that to an evaluator node. All right, good. So let's get back to the if condition over here. As I said before, we're working on arrays and we're not using an if condition for graphs. We're using a masking, which is briefly described in the other tutorial about arrays. Masking is a concept working first on a condition, which is the less than condition. So let's check it out. If it exists, condition less than. So we can plug in here two arrays and return getting a mask, which decide in which cases the element of the area of the first array are less than the arrays of the second one. What are we comparing? We're comparing here the distance, which we got over here, the subtraction of the particle position with the sphere radius. So we plug that in here and we compare that to the sphere's radius we have determined over here. So this results in the mask deciding which particles are within the sphere. To use that mask, we use the mask mix, array num mix node, plug in the mask and mix the arrays. What do we mix? Well, if the mask is 0, that means that the radius is not less, that the particle distance is not less than the radius. So we set simply the original particle position. But in the case that the mask is true, we set our new determined particle position. And sorry, here's my mistake. We use the length and not the subtraction to check. All right, this mixing basically is the if condition. So let me colorize that part of the graph reddish to point that out. And finally, the new position we set in the particle set channel. Well, the particle set channel over here needs the particle system, which we have determined over here. And maybe I clean up the graph slightly, that the whole thing is more separated. Okay, the only thing is missing is the path through node we got over here. Let me add another path through node and move that over here. So what we need as an input over here is first the direction, and the direction basically is determined here by the subtraction of the particle's position and the sphere's radius. So we can plug in that. Here we need the sphere's radius we have determined over here and the sphere's position which we got over here, and make it down, and that's what we got. Maybe we clean up the graph slightly, add another pass-through node to make the whole system more convincing. All right, this is what we got now over here. Okay, let's check out if everything is working like expected. Therefore, I deactivate the script script, so only the graph which we have created is executed. I reset the scene, and let's see. Well, we got an error over here. Set channel node input parameter 0. What's going on over here? We got our position. Node parameter is 0. Maybe we got a typo over here. Oh no, I totally forget to put in the get standard emitter. So put in the linear or 1 over here, and let's see what's happening. And as you might see now, the graph node system is doing exactly the same like the Python script before. Okay, let's push the memory. And there's one more thing I would like to demonstrate. I would like to show you how to use a real for loop within the graph node system, which is very similar to the for loop in the Python. Therefore, I create another script, copy in the text of the other script, and let's say we want to have more spheres than the one I'm showing over here. I created before a bunch of other spheres, so let's activate them. Here they are, and if we simulate the scene, you might see, okay, the first sphere is handled correctly, but the other spheres are not interacting with the liquid. So what I'm going to do now is first change the Python code to handle all the spheres in the scene, and that's pretty easy. We just command out the line over here where we get our scene object and add a for loop. Therefore, we loop over all spheres in the scene spheres, and scene spheres are basically, in this case, all the objects in the scene, since we only got spheres. Okay, these two lines and removing that line over there is basically doing the trick. We need some more spaces over here to give Python what it wants to see, kind of the brackets, where are the areas of the for loop. And now I'm quite sure it will work properly. So the first is handled correctly like before, and now the second one is handled correctly as well as all the other spheres within the scene. Okay, so finally I would like to show you how to do that with our graph system. Okay, let's go back to our graph system, activate it. As you might know from the other tutorials, for loops only can exist within a compound. So I create a compound for all the nodes in the scene, which make the scene much more smaller. And basically here's the part where we get the sphere or 1. So let's loop over all objects in the scene. Therefore we just get a node get all objects, exactly like in Python, get all objects. This returns us a node array of all objects. To know how many objects are in the scene, we use the array size node. This one tells us how many spheres are in the scene. Let's rescale the green area. Well, the get object node on this place we don't need anymore, so we disconnect it, and disconnecting means just removing the lines. This is similar to commenting out in Python. And so we add the for loop starting from 0, counting to the size of our array. So basically counting through all the spheres within the scene. And for each element, we need the get node array element of the array, and we access it within the for loop. So we connect that guy over here, and finally that's it. That's a for loop. We get all objects in a node array, get the size, loop through all the spheres within the scene, get that object, and the rest of the graph exactly stays the same. So let's check out if this is working properly. Have I connected? Yeah, the graph is enabled, everything else is disabled. I read that's the scene, start the simulation, and hopefully now within the graph node system, every sphere is handled correctly as a collision object, as you might see here. Yeah, that's pretty much it. That's how to transform your Python code into a graph node system. I'm pretty sure if you have worked a few times with graph nodes, you start thinking in graph nodes and your workflow will improve immensely. Yeah, have fun. Thank you very much.